Again, welcome to operating system CS332 class. And this will be the final lectures on process description and control. And in these lectures, we're going to cover the concept of process creation. So once the operating system decides, for whatever reason, to create a new process, it can proceed as following. First, it assigns a unique process identifier to the new process. Again, at this time, the new entry is added to the primary process table, which contains one entry per process. Second, it will allocate space for the process. This includes all elements of the process image. The operating system must know how much space is needed for the private user address space, which will consist of the programs and data, and the user stack. These values can be assigned by default based on the type of process, or they can be set based on the user request at job creation time. Now, if a process is spawned by another process, the parent process can pass the needed values to the operating system as part of the process creation request. Now, if any existing address space is to be shared by this new process, then the appropriate linkage must be set up. Finally, the process or the space for a process control block must be allocated. Now, the third step will be to initialize the process control block. And this process identification portion contains the ID of this process plus other appropriate IDs, such as that of a parent process. The processor state information portion can typically be initialized with most entries 0, except for the program counter, which is normally set to the program entry point, and also the system stack pointers, which is set to define the process stack boundaries. Now, the process control information portion is initialized based on the standard default values plus attributes that have been requested for this process. For example, the process state will typically be initialized to ready or ready suspend. Now, the priority may be set by default to the lowest priority unless an explicit request is made for higher priority. So initially, the process may own no resources or I/O device or files unless there's an explicit request for this, or unless they are inherited from the parent. So again, those are the steps. Assign a unique process identifier to the new process, allocate a space for the process, initialize the process control block, and set the appropriate linkages. Then create or expand the other structures. So mechanism for interrupting the execution of a process. Here we have the interrupt, and also trap, and also the supervised call. So we can set the appropriate linkage. For example, if the operating system maintains each schedule queue as a linked list, then the new process must be put in the ready or ready suspend list. Now, to create or expand other data structures. For example, the operating system may maintain an accounting information on each process to be used subsequently for billing or performance assessment purposes. Now, a process switch may occur only at any time that the operating system has gained control from the currently running process. So first here we have the mechanism, as we said, we have interrupt, which is the cause will be external to the execution of the current instruction, and also reaction to an asynchronous external event. We also have the trap, which normally associated with the execution of current instruction and the cause, and also the use will be handling of an error or an exception condition. Then supervised call is for explicit requests and use to call to an operating system function. So first, let's consider the interrupt, system interrupt. Actually, we can again distinguish, as many systems do, two kinds of system interrupts. One of which is simply referred to as an interrupt and the other as a trap. So the former, which is the interrupt, is due to some sort of event that is external to and independent of the current running process, such as the compression of an I/O operation. The trap normally related to an error or exception condition generated within the currently running process, such as illegal file access attempt. So with an ordinary interrupt, control is first transferred to an interrupt handler, which does some basic housekeeping and then branches to an operating system routine that is concerned with the particular type of interrupt that has occurred. So example can include the following. Example can be, again, clock interrupt. A clock interrupt, the operating system here will determine whether the currently running process has been executing for the maximum allowable unit of time, which is referred to as a time slice. So a time slice is the maximum amount of time that a process can execute before being interrupted. And next will be the I/O interrupt. Here, the operating system would determine what an I/O action has occurred. Now, if the I/O action constitutes an event for which one or more processes are waiting, then the operating system moves all of the corresponding block process to the ready state. So the operating system must then decide whether to resume execution of the process currently in the running state or to preempt that process for higher priority ready process. We also have a memory fault. In a memory fault, the processor encounters a virtual memory address reference for a word that is not in main memory. So if a processor encounters a virtual memory address, and when it's references for a word that is not in the main memory, so the operating system must bring it in the block, other page or segment of memory containing the references from secondary memory to main memory. Now, after the I/O request is issued to bring in the block of memory, the process with the memory fault is placed in the block state. So the operating system here then performs a process switch to resume execution of another process. Now, with a trap, the operating system determines if the error or exception condition is fatal. If so, then the currently running process is moved to the exit state and a process switch occurs. If not, then the action of the operating system will depend on the nature of the error and the design of the operating system. So again, in lecture 1 or chapter 1 of our course textbook, we discussed the inclusion of interrupt stage as part of the instruction cycle. So we can recall that in the interrupt stage, the processor checks to see if any interrupts are pending, indicated by the presence of an interrupt signal. Now, if no interrupts are pending, then the processor proceed to fetch stage and fetches the next instruction of the current program in the current process. Now, if an interrupt is pending, then the process must do the following. At least first, it must set the program counter to the starting address of an interrupt handler program. Then it switches from user mode to kernel mode so that the interrupt processing code may include privilege instruction. So the processor now can proceed to the fetch stage and fetches the first instruction of the interrupt handler program, which will service the interrupt. At this point, typically, the context of the process that has been interrupted is saved into that process. So again, as we said, the trap is normally an error or exception condition generated within the currently running process. So the OS must determine if the condition is fatal. But interrupt normally is due to some sort of event that is external to and independent of currently running process. And we went through the 3 examples here: clock interrupt, IO interrupt, and also the memory fault. And we also have the mode switching. So normally it is clear that when the mode switch is a concept that is again distinct from that of a process switch. So again, it's very clear then that the mode switch is a concept that is again different from that of a process switch. The mode switch may occur without changing the state of the process that is currently running in the running state. So in that case, the context saving and subsequent restorer involve little overhead. However, if the current running process is to be moved to another state, such as ready or block, etc., then the operating system must make a substantial changes in its environment. So the steps involved again in the full process switch are as following. First, we need to save the context of the processor, including program counter and other registers. Also, secondly, we need to update the process control block of the process that is currently in the running state. This can include changing the state of the process to one of the following other states. It can be ready, block, ready, suspend, or exit. Other relevant fields must also be updated, including the reason for leaving the running state and also the accounting information. So if no interrupts are pending, as we said, pending the processor, then we need to proceed to the fetch state and fetches the next instruction of the current program in the current state. Now, if an interrupt is pending, then the processor have to do these 2 items again, 2 steps. First, set the program counter to the starting address of the interrupt handling program, then switches from user mode to the kernel mode. So there's changes of process state, as we said there. The steps the full process switches are: first, save the context of the processor, then update the process control block of the process currently running the running state. Then move the process control block of this process to the appropriate queue. Then we select another process for execution. Update the process control block of the process selected. Then we also have to update the memory management data structure. Then we restore the context of the processor to that which existed at the time the selected process was last switched out. And as we mentioned earlier again, if the current running process is to be moved to another state, then the operating system must make a substantial changes in its environment. So that's execution of, again, operating system. So again, one traditional approach, common on many old operating systems is to execute the kernel of the operating system outside of any process. Now, within this approach, when the currently running process is interrupted or issues a supervisor call, the mode context of this process is saved and control is passed to the kernel. So again, the operating system has its own region of memory to use and its own system stack for controlling procedural calls and also returns. So normally, again, the operating system can perform any desired functions and also restore the context of the interrupted process, which causes execution to resume in the interrupted user process. The operating system also can complete the function of saving the environment of the process and proceed to schedule and dispatch another process. Whether this happens depends on the reason for the interruption and also the circumstances at that time. So mostly in any case, the key point here is that the concept of process is considered to apply only to user programs. So operating system code is executed as a separate entity that operates in a privileged mode. So execution again within the user process. Here, an alternative that is common with operating system on smaller computers such as PC or workstations is to execute virtually all the operating system software in the context of its user process. So the view is that the operating system is primarily a collection of routines that the user calls to perform various functions executed within the environment of the user process. And this shown at the diagram here. So at any given point, the operating system is managing n process images. And also each image includes not only the region illustrated, but also the program, as we can see the program, the data, the stack areas for the kernel program. So we have the process identification, process state information, process control information, then the user stack, also the private user address space, such as programs, data, where it is, and the kernel stack, and also share address space. This is again execution within, again, the user process. Now, most processes-based operating system uses a different, another alternative is to implement the operating system as a collection of system process. And this would be a process-based operating system. So as in the other opinions, the software that is part of the kernel executes in the kernel mode. In this case, however, major kernel functions are organized as a separate processes. Again, there must be a small amount of process switching code that is executed outside of any process. The approach has several advantages. One of them is it imposes a program design discipline that encourages the use of modular operating system with minimal or clean interfaces between the modules. In addition, also some non-critical operating system functions are conveniently implemented as a separate process. A very good example will be, we mentioned earlier, a monitor programs that records the level of utilization of various resources, such as memory, processor, or channels, and also the state of progress of user process in the system. Now, because this program does not provide particular service to any active process, it can only be invoked by the operating system. So as a process, a function can run at a assigned priority level and also being interleaved within other process under dispatcher control. So finally, again, here we can come to a conclusion that implementing the operating system as a set of processes is useful in multi-processor or multi-computer environment, in which some of the operating system services can be shipped out to a dedicated processors. And this can also, again, improve performance. We also discussed about the Unix is a very good example here. We know that, again, Unix system makes use of simple, but again, powerful process facility that is highly visible to the user. So Unix follow the model in which, again, most of the operating system execute within the environment of a user process. And also Unix uses two categories of process, the system process and also the user process. So system process run in a kernel and also execute operating system code to perform administrative and housekeeping function, such as allocation of memory or process swapping. But the user process operates in user mode to execute user programs and utilities, and in the kernel mode to execute instructions that belongs to the kernel. So again, a user process enter kernel mode by issue a system call when an exception is generated. So a user process, again, operate in a user mode or execute user programs and utilities, whereas operate in kernel mode to execute instructions that belong to the kernel. So again, a total of 9 processes that are recognized by Unix SVR for operating system is listed here. So this is again Unix process states. We have the user running, which executing in a user mode. Then the kernel running, the process execute in kernel mode. We also have ready to run in memory, which is ready to run as soon as the kernel schedule it. And asleep in memory means unable to execute until an event occurs. Process is in a main memory, but it's in a block state. Also, we have ready to run and swap, which is process is ready to run, but the swapper must swipe the process into main memory before the kernel can schedule it to execute. Then we also have sleeping swapped, which means the process is awaiting an event and must be swapped to a secondary storage or a block state. Then we have the preempted. The process is running from kernel to user mode, but the kernel preempts it and does a process switch to schedule another process. The next state will be the created. A process is newly created and not yet ready to run. Then we have the zombie. A process no longer exists, but leaves a record for its parent process to collect. So those are, again, the Unix 9-unit process states. So here also we have the process control. Here we say that, again, a process creation in Unix is made by means of a kernel system call, which we normally call the fork. So process creation by means of kernel system called a fork. That's in Unix. Now, when a process issues a fork request, the operating system performs the following function. So these are the functions. First, it will allocate a slot in the process table for the new process. Then also it assigns a unique process ID to the child process. Then thirdly, it makes a copy of the process image to the parent with the exception of any shared memory. Then it increments the counters for any files owned by the parent to reflect that an additional process now also owns those files. Then it assigns the child process to the ready to run state. Then it will return the ID number of the child to the parent process and a 0 value to the child process. So those are, again, the steps for process creation, again, the Unix system. So after creation, when the kernel has completed this function, it can do one of the following as part of dispatcher routine. So first, again, it can stay in the parent process. Control returns to user mode at the point of the fork call of the parent. Also, you can transfer controls to the child process. Here, the child process begins executing at the same point in the code as the parent, and namely at the return from the fork call. Then lastly, it transfers the control to another process. Both the parent, again, and the child are left in the ready to run state. So this will be the conclusion of our lectures in chapter 3 of our course textbook, which is the process, control, and description. And the chapter 3 will break the lectures into 3 different parts. In this part, again, we talk about the process creation steps. And also we use the Unix example also. So again, wish everybody the best. If you have any question, you can send an email or you can post your question in the Canvas. So I will see you in the next class. Thank you.